welcome to yet another WJEC A-level physics question. This was from May 2009's Unit 2, and it was actually the very first question on lasers. It was question 5 from that paper. Well, I say the first question on lasers in the new spec anyway. So we're given a simplified energy level diagram for the amplifying medium in a type of laser. They give a name to it. We're not particularly worried about what that name is. Let me just turn pen mode on. So it's a standard 4-level laser system, and for part A of the question we've got the very easy 3 marks of calculating the wavelength of the radiation emitted. So what we're going to use here is basically that lambda is hc over delta E. Remember that that's not given in the data book, so you will need to know it. So h is 6.63 times 10 to the minus 34, c is 3 times 10 to the 8. And the delta E is the difference between the two energy levels that we're looking at, which is levels A and B. And if we just look at the digits there, it's fairly clear that that difference is 1.9 times 10 to the minus 19 joules. So put those numbers into a calculator. And we end up with the answer of basically 1050 nanometers. Worthwhile putting the answer in nanometers, because that way then it makes the next part of the question, identifying the region of the electromagnetic spectrum in which that radiation lies, that much easier. 1050 nanometers is a little bit past the sort of 700-ish nanometer red end of the spectrum, so this is just infrared radiation or IR radiation. Next part of the question says that the radiation is produced by stimulated emission, and we've got to explain what we mean by stimulated emission, and we should include photon energy and phase in the answer. So with stimulated emission, a passing photon, try to avoid saying things about this photon being absorbed or anything, but this passing photon must have the right amount of energy. And the energy is going to be that 1.9 times 10 to the minus 19 joules that we saw in part A of the question, the difference between levels A and B. What it will do is it will cause our electron that's in level A to drop down to level B. And in so doing, a photon is emitted. Now this photon that's emitted has exactly the same energy, phase, wavelength, frequency, polarization, direction. It's basically absolutely identical to the passing photon. So a photon's emitted that is identical to the passing photon. Including energy in a phase. The question then asks us to explain briefly in terms of photons why stimulated emission gives rise to light amplification. Well, we started off with one passing photon, and we've ended up with 2 photons. So simply we've doubled the number of photons, and this keeps on happening every time stimulated emission occurs. Part B1, we're asked to referring to levels A and B to explain what is meant by population inversion. So simply we're going to say that there's going to be more electrons in level A than B. Which is the opposite of what we would normally find. Next, we're asked to explain why population inversion is needed for the laser to work. So here we simply have the idea that with population inversion in place, stimulated emission is a more likely event than absorption. Now, what that basically means is that in absorption we actually lose a photon. In stimulated emission we gain a photon. So for our laser to actually amplify the amount of light, amplify the number of photons, we need that stimulated emission to happen more often than absorption. Finally, in this 4-level laser system, level B is above the ground state, and we've got to explain how this makes population inversion easier to establish than in a 3-level system. Well, that level B is self-emptying. It empties very quickly. And it empties by the process of spontaneous emission. But the point is that leaves that level almost always empty. And consequently, we only need a few electrons in level A to get population inversion. So it makes this much easier to get and maintain population inversion. Thank you for listening, and please remember to like and subscribe.